So the empirical derivation brought us to a graph of displacement versus time squared. And we found that the slope, the constant of proportionality, should be equal to 1/2 g sine theta. We have two equations on the plot. One equation was from our experiment, from our data, and it gave us a slope with meters per second squared times t squared plus an intercept in meters. And the prediction, or the theoretical line, was simply a slope times t squared. The two slopes from our data and our prediction should be pretty similar to one another. In this movie, we're going to look at finding our value for g and the error analysis, the uncertainty propagation, and then conclusions. So let's just start right off with finding my value for g, and I'd like you to find your value for g. Here's the equation. 0.188 meter per second squared times t squared plus 0.030 meters. That's my equation. You'll have a different slope and a different intercept. Now, my slope was this value, 0.188 meters per second squared. But the theory says that the slope should be equal to 1/2 g sine theta, or 1/2 g h over L. So we can take your slope and set it equal to 1/2 g sine theta. And I'd like you to do that now and solve for g experimental, or g from my data. G from my data should be my slope times 2 divided by sine theta, just simply rearranging this equation. So when I plug in my value for sine theta, 0.0354, and I plug in my value for slope, 0.188 meters per second squared, I double my slope and divide by sine theta, I get g for my data is 10.621468927 blah, 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 meter per second squared. Now, hopefully you see two problems right away. The first one is pretty obvious. I cannot quote that many significant figures in my value for g. And secondly, I cannot state g absolutely. There has to be uncertainty in g, and yet I have not indicated how well I know this value for g. Now, we're going to get into that, but first, let's ask the grand question for today. Is my g, and you should substitute that for your g, maybe yours is 9.6 or 11.1, whatever it is my g consistent with the accepted g within the confines of my measurement uncertainties? What do we mean by that? Let's take a look at a graphic. And by the way, you'll be building this very graphic with your data and with your uncertainties and with your discrepancy. Here's my g sitting at 10.6. And I know my g to within plus or minus 0.5 meters per second squared. In other words, I cannot say that my g was absolutely 10.6. My g could have been anywhere from 10.1 to 11.1 based upon my measurement uncertainties, which had a 5% spread around my value for g. The real g is sitting outside the confines of my measurement uncertainties. It's sitting over here at 9.8 meters per second squared. And in fact, between my g of 10.6 and the accepted g of 9.8, there's an 8% discrepancy. The answer to this question of consistency for my data, I'd have to say no. My g is not consistent with the accepted g because the confines of my measurement uncertainties do not allow the accepted g to fall within those confines of my measurement uncertainties. So maybe if instead of 10.6 I had 10.2, then this g would be sitting inside these uncertainty bars. We'll talk about how to build this graphic and how to answer that question. To build this graphic, we're going to need essentially three key components. First of all, we're going to need the uncertainty in our value for g. So I have reported here plus or minus 0.5 meters per second squared. How did I find that number? How do I know the uncertainty in g? It's found from adding the relative uncertainties of each measurement that went into finding g. We'll go into that in more detail. Secondly, I'm going to need to know the precision to which we state the value of g. Is it 10.6 or is it Where's that slide where I had that written out? Sorry about this. Oh, here. Oh, sorry about this. I'm a little bit confused here. Is it the 10.6 or is it 10.62 or is it 10.621 or what precision do we measure G to? And we're going to find this by evaluating the resolution of our one significant figure uncertainty. So this uncertainty could have been plus or minus 0.05, in which case we would quote one more decimal place here, 10.62, or whatever that number was. And thirdly, we need to know the discrepancy between our G and the accepted G. And we find that by simply finding the difference in G's absolute value, divide that difference by the accepted G. In Denver, it's 9.80 meters per second squared, and we multiply by 100%. Now, getting back to the first one, how do we find that uncertainty in G? Okay, I have 0.5 listed here, but how can we calculate a number for your data? Just to recap, here's my value for G, 10.6214 blah, 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 meters per second squared. Question number 1, what precision do I need? How many sig figs do I quote? And secondly, the uncertainty. The uncertainty must be stated with my value for G. Otherwise, I'm declaring to the world that I know G absolutely. I don't. So I have to say plus or minus my uncertainty. Now, first we need to answer the uncertainty question. Then we can know the precision for which to report our value for G. So we have to answer this question first of the uncertainty. And that will tell us what decimal we can measure our actual G. Now, it might be nice if we could simply add the uncertainty from each measurement and call that summation the uncertainty in G. But there's a problem. I cannot add meters and seconds squared and centimeter together. These are different units, different measurement types. But I can sum the relative uncertainties. They are dimensionless, yet this will not give me the measurement uncertainty in my G. It will, however, give me the relative uncertainty in my G. Remember what a relative uncertainty is? It simply relates the uncertainty to the measurement. I have some uncertainty in my measurement, and I divide by my measurement. Multiply by 100%. Notice a few things. First of all, if I have an uncertainty in measurement and divide by measurement, my result of the ratio should be dimensionless because I have unit divided by the same unit. You have to be careful that you have both of these in the same unit. Something else I'd like you to note is this is a Greek letter. It's a small case delta, and we take that to mean the uncertainty. Capital delta often means a difference, where lowercase delta can mean a small difference. Now, getting back to this statement that I sum the relative uncertainties, here we have the sum of the relative uncertainties. To find the relative uncertainty in G, so this is a dimensionless number, it's simply the sum of my relative uncertainty in height, length, displacement, and twice the relative uncertainty in time. If you remember, we squared the time, and that means we have to double the uncertainty in time. So let's talk about each of these relative uncertainties. We measured height of the block and length between the supports. Those two together gave us sine theta. And each of those has their own relative uncertainty. We take the uncertainty in length and divide by the length. The uncertainty in displacement divided by the displacement, and so on and so forth. To find the relative uncertainty in G, we sum all of these up. But we need to find what each individual component is. What is each term? The delta H over H we'll evaluate first. So to find the uncertainty in H divided by H, first we find the uncertainty in H, which is simply the resolution of the vernier caliper. The uncertainty in H for this experiment is 0.005 centimeters. Now that tips me off that I'm going to measure h also in centimeters. H is the height of the block, and from my experiment I got 3.500 centimeters. Notice that I match the number of decimal places of my reporting of h with the uncertainty in h. The precision here needs to match the precision here. The uncertainty in h divided by h, I finally find that to be 0.1%. I multiply by 100% my ratio. And so I can state h is equal to 3.500 centimeters plus or minus 0.1%. You're going to report this on the post lab when you're asked to state all your measurements by name, sample value, the uncertainty, and then in parentheses you're going to write how you got the uncertainty. So in parentheses here on the post lab I would say this came from the resolution of the vernier caliper. So that's delta H over H. It's 0.1%. So that's going to be added to all the other percentages that went into finding delta G over G. Now since we have this value for H with uncertainty, go ahead and put that into your data table. I think it's on page 2 maybe. Find it, the height of the block, report it, and report the uncertainty and the relative uncertainty, and then state it came from the resolution of the vernier caliper. Next we'll build delta L over L, the distance between the supports, that length. Delta L is a 2-point measurement. Do you remember that? Because there were 2 legs on the track, and there was parallax with each of those measurements. And you may have gotten a different value, but I got delta L is plus or minus 0.4 centimeters, or plus or minus 4 millimeters. But I want to keep the units the same, the dimensions the same as my length. And the length is, L is just the length between the supports. And here for mine it was 99 centimeters, but I reported as 99.0 in order to match the precision of my uncertainty. Delta L over L. I calculate that by 0.4 centimeters divided by 99 centimeters times 100%, and I get plus or minus 0.4%. The uncertainty in H was quite a bit less, 0.1. It was 4 times smaller. Or my uncertainty in length is 4 times greater. So I report length is 99.0 centimeters plus or minus 0.4%, and then in parentheses on the post lab I would state that this is a 2-point measurement with parallax. And we want to record that value for the distance and the uncertainty and the relative uncertainty as a percentage on your data table. And don't forget to state how you got the uncertainty. It was the 2-point measurement with parallax. So next we will build, I need to mention quickly that H, if you remember height, the block, and the distance between the supports, H over L was sine theta. Now sine theta, we find this measurement uncertainty a little bit differently. If you remember, the uncertainty in sine theta divided by sine theta should simply be the sum of the relative uncertainties that went into finding sine theta, namely H and L. So if I take this sine theta down here and multiply it by that sum of the relative uncertainties, I can find the measurement uncertainty in sine theta. In other words, my sine theta times delta H over H plus delta L over L. Take that sum and multiply it by sine theta. So in other words, I take the 0.1 and the 0.4% and I get 0.5% when I sum those. Take that 0.5% and multiply it by my sine theta. That gives me my measurement uncertainty. So you can record those in your data table and simply write, it's the sum of the relative uncertainties in H and L. Continuing this question of what is my value for G in terms of uncertainties. Delta displacement over displacement. What do I use for delta displacement? What is my uncertainty in the displacement? Well, it was a 2-point measurement with parallax, and there was motion. If you remember, my displacement had a start and a finish position, and therefore a start uncertainty and a finish uncertainty, or final uncertainty. And those two values for uncertainty were probably a little bit different, but they summed in my experiment to be about 7 millimeters, or 0.007 meters. Displacement is simply start minus final position. And I will use average displacement for my measurement. So in other words, I'll look at my data table and just average all the displacements and get 0.85 meters. So I record my uncertainty in displacement divided by displacement, my relative uncertainty, as 0.85 meters divided by 0.007 meters times 100% plus or minus 0.8%. And I state my displacement with a sample value, my uncertainty, and then in parentheses I would say it was a 2-point measurement with parallax and motion. I'd write that on my post lab. And I'm going to record all these values in my data table. There's quite a bit here. The final position, I was calling that finish. Sorry about that. The final position with the uncertainty, and it was a 1-point measurement with motion. I guess I should have said parallax and motion. And here we have start position uncertainty. Okay, and that was a 1-point measurement with parallax. And then I add those measurement uncertainties to find the measurement uncertainty in my average displacement. And I take that measurement uncertainty and divide by my average displacement to get the relative uncertainty in displacement. And we remind ourselves that the uncertainty in displacement is the uncertainty in start plus the uncertainty in the final position. And finally, this is probably the most difficult one. We're dealing with the uncertainty in time divided by time. The time in the denominator is simply going to be the average t from all the t averages. Okay, we'll look at the data table in just a second. The uncertainty in t, however, is the standard deviation from 3 t's found at maybe the average t, or we'll have another option. We'll talk about that. In other words, the uncertainty in time is the standard deviation, the sigma, of t1, t2, and t3. And from my data, I get plus or minus 0.04 seconds. So when I analyze this relative uncertainty, I take my average time of 1.98 seconds and divide by my uncertainty in time, 100%, and I get plus or minus 2%. That's quite a bit larger than the other components, the other terms here of uncertainty in H, L, and D. And I report my t average as 1.98 seconds plus or minus 2%, and on the post lab I'd add a parenthetical here to say the uncertainty was from the standard deviation of 3 values for t. Now how do we find the average time? You can just simply take all your average times and average them. Yeah, by average times, I mean each run had a T1, T2, and T3, and you found the average. Take all those averages and find the average of all those average. Okay, and I get about almost 2 seconds for my average. If you'd like, you can just go down to the middle of the data table and use that one. Now to find the uncertainty in time, we use the standard deviation. If you remember, the standard deviation of time would be the summation of the average time minus the individual time, T1, T2, and T3. Each of those differences squared, and then divide by the number of data points, that's 3 minus 1, and take the square root of that ratio. If we write that out more carefully, we get the t average. Let's say we're doing it for this run right here, 1.22. So it'd be 1.22 minus 1.25, and then square it, plus 1.22 minus 1.18 and square it, plus 1.22 minus 1.22 squared, and that one's 0. And we divide by 3 minus 1 because there's 3 data points. And then we take the square root. And so we state the uncertainty as plus or minus that standard deviation. Now, what I'd like you to do is just choose one of these runs that seems to have the worst in the spread of data. Okay? It doesn't have to be necessarily the worst, because maybe you have one that's just absolutely terrible. So just find a run. You can just choose one arbitrarily and then analyze those values. So just do the standard deviation once. I did it for every single one because I used a spreadsheet, but we want you to do this by hand. And you're going to record that in your data table, the time average for all the trials, the uncertainty, and then the relative uncertainty, and state that that was the standard deviation of T1 through T3. So at this point, we've built all the pieces of the relative uncertainty in G. We take each relative uncertainty and we sum them. We cannot forget that we have to double the time uncertainty because we've squared time in our analysis. So when I add up all those relative uncertainties, doubling the time, I get 5%. And it's important that we state this as one significant figure for our uncertainty. So I'm not going to say 5.296%. I'm going to just state this as 5%. So now we know how we can build this value. The 5% comes from the sum of those relative uncertainties. How do we get the plus or minus 0.5 meter per second squared? Well, we can take 5% of our huge number of sig figs, okay, our value for G. Maybe you had 9.3, 2946, whatever. You take 5% of that, and I get 0.531 meter per second squared. Remember, we only want one significant figure for our uncertainties. So I'm going to state my uncertainty as 0.5 meter per second squared. Or I could state it as plus or minus 5%. So I state my value for G as being 10.6 meters per second squared plus or minus 0.5 meter per second squared. We know G to the 10th place because that is where our uncertainty lies. So I know that I report G just to the 10th place. And here I've rounded 10.62 to simply 10.6. On the post-lab, you'll finish your discussion of measurements and uncertainties by stating your value for G, the uncertainty in G, and then you'll write out this summation here. You'll actually write out delta H over H plus delta L over L, so on and so forth. And that will finish that particular post-lab question. To find the percent discrepancy. Oh, and by the way, this value here for uncertainty in G allows you to build these bars away from your value of G. So you can draw your line showing all the possible values for G, mark out where your G lies, and then draw your error bars approximately as big as they need to be to show the spread. Mine went from 10.1 to 11.1, but yours, of course, will be different. To find that discrepancy, that in my example it was 8%, we simply take the difference of these two G's, the absolute value, and divide by the accepted. And I get 8%, you'll get something a little bit different. So at this point, you can take a break, pause the movie, and I'd like you to draw out this graphic. There should be room on your data table for this, or just use a separate page. If you have 9.2, of course, your drawing here is going to be to the left of G. If your G is larger than 9.8, it's going to be like mine, to the right. And try to do your best. See, I have 5% spread here, so this represents, and it's plus or minus 5%. So from 10.6 down to 10.1, that represents 5% of 10.6. And then I have another 3%, spread. And that's why I have to say that my G is not consistent with the accepted G, because the accepted G is sitting outside the confines of my measurement uncertainties. Now watch out. There's a little game that you can play, and we don't want you to do this scientifically. If you said, I have 8% discrepancy, but my uncertainty in G is 23%, then this G right here would certainly sit inside the error bars. So that's a little game that you don't want to play. You don't want to try to stretch out your error bars so that the real G fits inside. You need to be honest. You need to take data with integrity and analyze those error propagations carefully, okay, so that you're reporting accurately how big those bars are. It's better to say that my G is not consistent than to say that I'm such a poor experimenter that my uncertainties are about 23%. Now, what were the contributing factors that made my value for G to be so far away from the accepted value for G? I wasn't consistent with the real value for G, but why not? Why wasn't I consistent? At this point, it's just simply looking at each of your measurements and where are the largest problems. H may have had problems. Maybe the table was not level. Think about it. An unlevel table could drastically change H. Delta H was pretty good, but H itself may have been drastically different than the real value for H, because if my table was unlevel, I would have to add to my block height, whatever the unlevel height was of the table. D, the displacement, could have been measured with less uncertainty if I had, say, laser gates. So as soon as I released the glider, there'd be a laser gate tripped and a timer would start. And then as soon as the glider got to the final position at the bottom, there'd be another laser gate. There seems to be a real problem here with the time. We're doubling time, and then time is large to begin with. By time, I mean the uncertainty in time. So we have 4% here. That would probably be reduced drastically with, again, laser gates. So what's due next week? Well, we have data and graphs write-up. You need to make sure that you complete everything that's on the cover sheet and use the order shown in the table of contents that's on the cover sheet. There's going to be one write-up per group or per lab station. So make sure that you choose whoever has the nicest handwriting. All the work that we did in this movie, you'll find places in the write-up to record these things. And then you have the next pre-lab. That's due. And then you should print out the next post-lab to have it in class. Oh, wait. If your next post-lab is 1D motion, that post-lab is actually in your manual already. So I hope this has helped you build this graphic to describe the consistency between your G and the accepted G.